It's a great pleasure to be here. And indeed, I would hope to share some of the most recent results on other mechanisms of violating thermalization, at least in a weak sense. I mean, motivation comes from many artificial systems or many toys for physicists that are being realized in the lab. And some of these all of these toys, right, people try to isolate them as well as possible from the environment, but then it's not necessary, right, if you isolate the system from environment but cannot switch off interactions, as many of people here already explained in the lecture, system is going to be reaching thermal equilibrium on its own, right? And in that sense, long coherence times in terms of isolation from environment doesn't promise you that you're going to see some new physics immediately in such a system. And again, as many people explained, conventionally, we would be believed to be in the thermalizing domain, right? If you prepare a highly excited state of some typical interacting system, you'll see ballistic growth of entanglement. Your eigenstates from eigenstate thermalization hypothesis will have a lot of entanglement, and a lot of other properties will follow. I tried to explain something about many-body localization, which is a kind of different scenario, right? When your entanglement spreads logarithmically slow, all of your eigenstates are more or less product states twisted by quasi-local unitaries. There is a number of emergent conserved quantities. So now kind of question is anything, the question of today's talk is something beyond these two guys. But actually, again, just show you an experiment. I didn't have a chance to show it in my lectures, right? This is an experiment on entanglement growth in an MBL system. And people are able to measure in some almost direct way entanglement contribution. And you see it grows here as a log t. That may be convincing, maybe not so convincing. But what's interesting is that if you reduce this experiment without disorder, all interesting dynamics is going to end up here. Right? So you don't need the system. You don't need all this isolation. All dynamics, entanglement will shoot up to the sky here. And that would be the end of the story. Right? And that's kind of one example of how escaping thermalization gives you interesting dynamics on a long time scale. Now, today, again, we will try to see roots to long time coherent dynamics without disorder. And inspiration comes from experiment in Harvard who realized a bunch of trapped two-level systems. And again, for me, these are just two-level systems. And once this kind of Rydberg atom is in excited state, what it does, it interacts quite strongly with its neighbors. It's dipole-dipole interaction, so it's very fast. It has very fast decay. But what it does, if you shine laser resonant between transition, if there is an atom in excited state, it's going to shift energy levels of nearest neighbors, and it's going to lead to this dynamical Rydberg blockade, right? So the idea is that such configuration is in principle allowed, but if you start from state with no Rydberg, such configuration cannot be reached dynamically, right? So in some sense, in a dynamical sense, this model has a Rydberg blockade of having no two black dots next to each other. And what experiment showed is that there is an atypicality in this model, that some states would feature long-time oscillations and some states would feature rapid relaxation. Now, kind of as a theorist approximation, again, model has other terms, but starting just how to think about it, it's a bit of a weird model because constraints destroys product state structure of a Hilbert space, right? I removed all states which cannot be reached dynamically. Those states are in principle are still there, but since dynamics never explores them, I can remove the states. For example, this state is removed, and you see that the Hilbert space already scales not like a power of some integer number, like 2 to the n, which would be for normal spin-half systems. It would be a Fibonacci number. Now, Hamiltonian is a very simple matrix in this Hilbert space, right? It's a matrix which has basically, which says that each atom tries to flip its state, right, from black to white, from white to black, only if its all neighbors are not excited. Right? That's a very simple kind of two projectors onto ground state or onto ground state, and then Pauli X matrix. Now, this Hilbert space plus Hamiltonian is actually a graph, if you think. Again, this is purely of diagonal matrix with all elements being 1, and vertices label my configurations of Rydberg atoms. And again, just an example, you start with this configuration, which is very interesting because it gives rise to long-time oscillations. And your Hamiltonian tries to, it cannot create any new excitations, right, because there is a blockade. What it tries, it removes one excitation, you go here, you can remove another excitation, maybe you remove all excitations, and so on, right? So this many-body problem is now would be mapped on a single particle living on such a graph, right, if you wish. And now, if you try to do numerical simulation following up what was done in experiment, you see that first, okay, entanglement from whatever state you start grows ballistically. So again, hopefully no many-body localization here. Again, it's a clean, non-disordered model. Would be very crazy to expect some sort of localization. But you see there is already in the entanglement growth, there is quite a lot of atypicality, right? You see that the slopes of the curves are very, very different. Moreover, for this Z2 state, you see some long-time oscillations in entanglement, and you see some long-time oscillations in local observables. Now you see, now you try to do even more drastic measure of kind of atypicality. You ask about return probability. So I take that huge graph for some big system, and that graph blows up exponentially. Prepare one product state configuration and ask what is the probability of returning to the very same product state, right? And if you expect ergodicity, you spread over the graph and never come back. And that's, for example, what's going to be happening for the Z4 state. So if I have a density wave with a period 4, Rydberg, three sides in the ground state, then Rydberg again, and so on, you see that this line is kind of invisible. It's a magenta line. It kind of goes down to the noise floor and just fluctuates there. Right? So that's what we expect in a normal system. You prepare a product state and system kind of never comes back except for some fluctuations, right? Now, other states like Z2 or Z3 show very different behavior. You see that again, there is a 70–80% probability of coming back to the very same product state, and it repeats again and again. This probability kind of decays, right? But this system seems to be having some atypicality for a specific set of states. And again, these many-body revivals are even much more spectacular than the slower than usual entanglement growth. And natural question comes, where do they come from? So the first part of the talk is about eigenstates. So those of you who like eigenstates, that's your part. Second part is going to be about dynamics, right? So if you are a fan of variational dynamics, hold on with your questions for a second part. But in terms of eigenstates, right, if you have oscillations, you expect a number that your initial state expands over a small number of eigenstates which have approximately commensurate energies, right? That's a very natural way to get an oscillations in the dynamics. And that's indeed what happens. If you just numerically check what is overlap of the Z2 state with all eigenstates. So here I plot ED results, right? I diagonalize all my spectrum. This is energy of eigenstate, and this is overlap. And you see that there are somehow, surprisingly, some small number of states which have very high overlaps with this with this state. And that's something, again, that is not expected in a random matrix theory or in an ETH case, right? In ETH case, your eigenstate should be pretty much similar to random vectors. And random vectors are not expected to have some regular structures in them and special overlaps. Moreover, surprise comes when you start looking at some thermalization probes, like entanglement entropy. This is a bipartite entanglement entropy of eigenstates, and density and color shows the density of points. And you see that, yeah, most of the points are concentrated up here, right? So here there is a high density of states, and your thermal entanglement tries to be your quantum entanglement. But now the very same 7 guys are hanging out, or 8 guys are hanging out low there, right? And they're somehow enjoying very low entanglement, whereas everybody else, there is exponential number of states at the very same energy who have a lot of entanglement, right? So that's kind of these states. These are what gives rise to quantum revivals and to these long-time oscillations. Now the question, where do these states come from, right? The phenomenology says that this model has at least L+1 eigenstates which seem to violate eigenstate thermalization. At the same time, a lot of other states kind of behave in conventional way, right, as you see. Again, and this looks approximately like parabola. This kind of fluctuations will get weaker for bigger and bigger system sizes. So, most of the states behave in semi-conventional way, but some guys enjoy protection. So where it's coming from? And this Hamiltonian, right, indeed looks like a collection of free spins, almost like a collection of free spins, right? There is a dressing of projectors. And it kind of suggests, let's try to play, right, with some sort of SU2 type structure. And you may say, okay, I have this graph. Let me split my Hamiltonian into raising and lowering operators. And raising operators will move me right on the graph, and lowering operators will move me left on the graph. So basically, a raising operator tries to flip spins in one direction on one sublattice, on even sublattice, and in another direction on an odd sublattice. And now you commute these two guys, and you recover something which smells very, very much like HZ operator, right? It's Pauli Z operators dressed by projectors. So you think you're one step away from from SU2 algebra, and you commute it again, and it doesn't close, right? So this guy has, at the operator level, it has these operators. You can try to commute it again, and it will get more and more terrible, right? As usual happens if you kind of many-body algebra doesn't close, it blows up usually pretty nasty. Okay, so SU2 algebra failed. Now, can we have a bit of more modest goal? Let's abandon the idea of full SU2 algebra. Let's build one SU2 representation. And we know where to build it from, right? I want to build it from this very much special, nice and beautiful state, which shows periodic oscillation in experiment. So I start my process. I act on it by raising operator. Raising operator propagates a defect. I apply back my lowering operator. Lowering operator has no choice but patch this defect because everybody else is blocked, right? There is a Rydberg blockade. I do it once again, it still works. And now at the third step, again, my SU2 algebra, even SU2 representation fails. But now I understand where it's failing from. Its failure comes exactly from these configurations when two defects kind of collide next to each other. And it's a bit easier to understand the failure by requiring that all the states are eigenstates of HZ. So this is eigenstate of HZ, this is eigenstate of HZ, and this number 2 already stops being an eigenstate of HZ, and problem again is caused by this configuration. There is an extra term, order 1. If you wish, all these guys have eigenvalue order L, but then this guy has a extra term order 1. So we got a problem, but we kind of know where it comes from, and that suggests that this problem may be fixable. And now we do something not very conventional. Instead of trying to deform maybe my initial state, we start deforming my algebra. So I keep my parent state, I keep my highest weight vector, and I try to realize a SU2 representation by deforming my algebra. So it's a bit of a nasty calculation, but I know what I'm doing, right? Because I know that the problem comes from this state when two defects are adjacent to each other, next nearest neighbors, so I kind of know what type of terms I want to introduce. I want to make my spin flip to interact with spins 2 sides away. That's kind of why I need such a term. Then you have 5 pages of algebra, and you arrive to a quadratic equation, which says that magnitude of this term must be this number. You check if it works, and indeed you see that this term, what is it doing to entanglement growth? That's entanglement growth in 24 sites in a quench. Without this term, entanglement grows slow and oscillates, but with this term, entanglement growth kind of almost goes away on the numerical time scales. It's tiny deviates here from this axis, but you see that this term kind of works, right? You added 5% deformation to your Hamiltonian, and that suddenly almost killed entanglement growth starting from your highest weight vector, from this Z2 state. So you know that that's hopefully a correct route. Right? There is another special point which we still don't understand. At approximately half of this deformation, entanglement growth still is pretty fast, but something else would happen. The level spacing ratios are going to be anomalous, and this model experiences some weird anomalies there, so that's something we still don't understand. But this point, again, comes from proximity to SU2, and now you patched problem in one place, you created problems in other places, because once you end this deformation, these terms become problematic. So with this term, you still don't get this second guy to be an eigenstate of HZ. Your SU2 algebra still fails at the same step. You can quantify this failure, and you see that it fails a bit better, a bit less, right? So error is smaller. But now you know that you need kind of all the string, right? Because again, patching this term causes problem in this term, patching this term would cause problem in here, and so on. So you add this whole string. Maybe one can solve it analytically. At this point, we kind of gave up on it, and what you can do, you can optimize it numerically. And computer spits you surprisingly exponentially decaying numbers, which kind of quite well are described by this approximate ansatz. So this is ansatz. I think crosses are some result of numerical optimization, and you see that they kind of behave reasonably well and are very close to each other. Right? So without requiring exponential decay of this perturbation, you still obtain from computer quasi-local exponentially decaying deformation of a Hamiltonian, and here is its effect. Right? So for example, fidelity revivals now become perfect up to 10 to the minus 7, and if that would be an ideal SU2, fidelity revival must become perfect, but we cannot really optimize it because we have a finite size system, we have a finite level spacing, we have a finite numerical precision. Entanglement growth, again, absolutely halts, but it not only halts, but you see that the leading non-zero singular eigenvalue is order 10 to the minus 2. It kind of comes back and forth, so it's not even everywhere, right? It kind of emerges and then decays again. And that's what it does to the special eigenstates. You see that their overlap with Z2 parent state is enhanced, and all other states kind of going down. again, if that would be an ideal SU2 deformation, these guys should have absolutely zero overlap. And these guys would have overlap described by certain formula from SU2 algebra, right? Again, we are not yet there, but conjecture is, looking at this data, that maybe with an infinite range perturbation, this model can be brought to an SU2 point. So that's, again, kind of intuition behind this model and behind the states, right? That the generic PXP model, if you wish, is a deformation of this ideal point, quite weak deformation because these terms are all exponentially decaying. You see that long-range terms are very small. And in some sense, if you believe in ideal SU2 representation, you can think about this model again as adding some deformation to it. And that's why these states are hybridized. In thermodynamic limits, they're not going to survive, but still you're going to have long-time oscillations because of, again, even if eigenstates are not surviving in thermodynamic limit, it doesn't mean that your dynamics is going to immediately become thermalizing. Surprisingly, this thing also carries out in 2D, at least in the reading order. And that's kind of another argument why it's probably not related to any kind of integrability, or again, to the best of my knowledge, I don't know any beta and Zatz integrability structures in 2D, but you can play a very similar game. In 2D, there is a maximally blocked Z2 state. There is an analog of PXP model. You add projectors on a cross, right? You block just your nearest neighbors. This model has, without any deformation, it has a bunch of high overlapping states, but you see things are much worse, right? 2D is much better for thermalization. You see that there are, for example, no clear entanglement outliers, right? There is a bit of low-lying weakly entangled states, but it's nothing to what was compared in 1D, right? Still, we have a perturbation which seems to stabilize, again, not as well as in 1D, but it seems to stabilize. It seems to pull down some low entangled states down here, right? So the story seems to be repeating. Again, it's much, much harder. Perturbation, you know, we have access to 6x6 systems. Our perturbation range is nearly half of your system size. So we cannot really push it to whatever, 32 sites, 32 by 32 lattice, and understand that have this conjecture as strong as in the previous case. But perhaps one can still realize this approximate embedded SU2 representation even in a two-dimensional model. And then that would mean actually perhaps any bipartite lattice, 3D, cubic lattice, and so on. So that's kind of first part of my talk, right? So these eigenstates can be viewed as or these eigenstates can be viewed, right, as a weakly broken embedded SU2 representation, right, which emerges in this model. And we don't have analytical solution, but the conjecture is that model which would have exact kind of parent model which would have exact scars would be weakly deformed PXP model, where this deformation is exponentially decaying. So that's kind of sort of end of the eigenstate story. And now let's kind of stop and ask, okay, eigenstates are complicated, right? What about variational picture of this whole business, right? Is it going to teach us something, and is it helpful? And again, Hilbert space life is complicated. You see, you start on this vertex, you leak there, then you start leaking back. And again, this graph must have some million of vertices, right? Not a small number of vertices because it's only 9 or 8 Rydbergs, right? So, you know, there is some funny bouncing in this graph, but dynamics is ridiculously simple, right? Dynamics is this. You have a two-side unit cell, and you oscillate from this state to this state, right? Or an experiment, you see again, that's experimental data. Oscillations are quite damped. They don't see that many oscillations, perhaps because of imperfections. Yes? Yes? Well, in some sense, I'm not aware of kind of getting the same SU2 algebra in any other arbitrary model. And here, something that is special, right, that these states are really scattered throughout the all many-body band. So actually, the most important state lives where you have the highest possible density of states, right? So in some sense, again, I think that's something. Of course, you can realize some sort of such scenario at low energies, right, when you have very low density of states. But what is interesting that these guys are kind of embedded everywhere and they're coexistent. But I mean, you are totally right. After you know this mechanism, I can write you now a family of toy Hamiltonians, which are going to have exactly the same phenomenology. Why PXP model, which is experimentally realizable, has no tuning parameters, is so close to this point, I have no idea. But again, I'll try to make case that indeed this is something more generic. So hopefully by the end of my talk, there'll be some case that it's a bit more generic. So I have these oscillations between two Niel states. Something, hardly anything can be simpler than that, right? And we do this beautiful machine, right, which kind of swallows my quantum Hamiltonian, uses some variational state, and spits me out classical equations of motion, right? And there are many kind of brands of this machine. You can do mean field, you can do cluster truncated Wigner approximation, you can do some Gaussian states. My favorite machine for this talk is this, TDVP based on matrix product states, right? And that was done actually first by Harvard team who proposed this matrix product state ansatz to describe dynamics of this PXP model. And that's nothing else but a projected mean field, right? You would like to do a mean field, but mean field has a problem. If you have two spins pointing at arbitrary directions, you would violate a constraint of no two spins being up to each other, up next to each other, right? That's a Rydberg blockade. If there is an up spin, which is Rydberg, next guy must be absolutely in a down state. And the way around it is to replace this product state by an MPS. And MPS uses very simple fact. There is still one angle, theta. It says probability of spin being up is sine theta, being down is cosine theta. But now the funny thing is that this up spin comes with a sigma plus matrix in an MPS. And if you have two sigma plus matrices next to each other, they're going to multiply and going to give you 0, right? So that's basically glamourized version of the mean field, which uses MPS structure to obey a constraint. So Harvard people did project this ansatz, did project quantum dynamics onto this ansatz. They obtained a nonlinear dynamical system of equation. And surprisingly, the system yields you a periodic trajectory. And this is exactly periodic trajectory which connects Z2 and Z2 prime states. So this phenomenon has a kind of variational explanation, right, in terms of this trajectory, which requires basically a two-side unit cell and would describe your oscillations. And that's what kind of gave actually name of this whole thing. And that what led kind of us to think about it as a generalization of quantum scars. And just as a reminder, very often people show this chaotic Bunimovich stadium, right, as an illustration of what chaotic dynamics is doing. And then you can study its quantum version. Quantum version is nothing else but Laplace operator, eigenvalue of Laplace operator number 10,000, for example, right? That's how it looks. Collection of plane waves, right? Some random collection of plane waves. Now you can ask, what happens with this weakly unstable periodic trajectories, right? I have a periodic trajectory which ball bouncing vertically, but if I slightly tilt it off this vertical bounce, you see it spending some time here, but then it's unstable. So it's hanging out around its original path for quite a long time, and hopefully you had patience, and now it's escaped, right? Now this ball is going to do the same as it was doing here. It's going to escape, explore all points of the stadium. So now, if you search through your eigenstates, suddenly you won't find an eigenstate, exact eigenstate of your Laplace operator, maybe number 10,100, which is going to look like this. Doesn't look random at all, right? Looks concentrated around place where you would have this unstable periodic trajectory. So again, that's the intuition that in a one particle system, unstable periodic trajectories may leave traces in a quantum version in the form of eigenstates, which are non-ergodic, right? This guy doesn't look like a collection of plane waves. It's actually concentrated around the unstable trajectory. So now we believe that something similar, right, is happening now in a quantum model. We don't have yet a very qualitative, very quantitative connection, but we believe that in this quantum model, we have on one hand side a bunch of non-ergodic eigenstates. We can show that those eigenstates will have anomalous participation ratios. They're going to be concentrated in a Hilbert space. On the other hand, they kind of describe dynamics of this collective Niel type oscillations, up, down, up, right? So there are kind of two ingredients. We can't really do, in order to connect them, right, it would be terrific to take this variational principle, kind of requantize it, and obtain this eigenstate somehow semi-classically. So that's a so far missing ingredient, but things match. That's on one hand side. On the other hand side, once you ask people about these billiards, right, people who do Hamiltonian chaos, they say, look, this billiard is absolutely fine-tuned. Normal Hamiltonian system must have not only unstable trajectory, it must have actually stable periodic trajectory. But of course, stable periodic trajectory occurs only in dimension of phase space bigger than 2. So that's kind of promoted us to do the same machine, right? But now we shift this ingredient. Instead of 2-side unit cell ansatz, as Harvard people did, we insert 3-side unit cell ansatz. And that would be ideal ansatz, for example, to describe Z3 oscillations, right? If you want to describe dynamics of such a state, right, that's enough. You need 3 angles. Then you need a very good postdoc to rotate this handle and get, some nasty equations of motion. But you're not actually interested in these equations of motion, right? What you are interested in understanding their behavior, and again, maybe a bit of review, how people do this. That was new for myself as well. You have this dynamical system of 3 variables. So it defines trajectories in a cube. Now you define something that is called Poincaré map. Namely, you choose a plane, for example, theta b equals 0, and you track when your dynamics is crossing the plane. Now you understand that if you have a periodic trajectory, it's going to give you stationary point of this map, right? Especially if I fix my derivative. Let's say I fix my derivative to be positive, then this periodic trajectory crossing my plane only 2 points, and it will give me this stationary point. If I have some orbit which lives near this trajectory and kind of winds on top of it, it's going to leave me a circle, right? Do you understand how that works, right? So now you do this numerically for this terrible set of differential equations, and that's what you recover. You indeed recover a Poincaré section with very clear mixed phase space nature, and you see a very big stable regions. Actually, all these big stable regions are symmetry related to each other. This model has a lot of symmetries, right? There is a 3-side unit cell. You can do inversions. You can do translations. Actually, practically speaking, there is only one most stable periodic trajectory, which is surrounded by this big, people would usually call this KAM type torus. And now you ask, okay, that's cool. It's classical, may not have anything to do with your quantum model, right? So you found this trajectory. Is it important at all? And the answer is that yes, it is. For example, we saw phenomenologically that Z3 product state has revivals. But actually, if you sit down in this trajectory, which is not Z3 product state, it's weakly entangled state, it shows you even better revivals. Or if you wish, this Z3 product state has entanglement growth, which is suppressed compared to some other points. But this periodic trajectory has even more suppressed entanglement growth. So actually, these trajectories, right, they are important, and they give you better notion of where to search for better reviving, right, and more stable, so to say, generalization of scars, right? So again, this Z3 product state turns out to be close to this periodic trajectory. But if you think who is the parent of my Z3 revivals, it's not actually Z3 product state, but would be this kind of torus. Yes? Yes. Yes, exactly. Well, that's, it comes, yes. I'm trying to make this claim, but now the question is that if you look closer in this phase paired portrait, you would find infinite number of periodic trajectories. And the question is, do we have infinite number of scars, or which of them are important? Right? So before that, let me just show you another example, which is, again, to some people maybe a bit more non-trivial, of the same machine. Now inserting here 2D Hamiltonian. And we are not able to solve for PEPs analytically, but we are able to define a tensor tree and solve an approximation of 2D variational dynamics analytically. We still obtain the system of equations which describes dynamics now on any bipartite lattice. You can take cubic lattice, you can take honeycomb lattice. As soon as it's bipartite, these guys describe it. And that describes what happens to quantum scars in presence of detuning. Right? If you add chemical potential, you can obtain that there is a trajectory which is basically getting deformed. So without chemical potential, you would be rotating exactly on this big meridian. Now chemical potential is effective magnetic Z field. It deforms you. And you still have non-trivial entanglement, right? Your variational dynamics still agrees pretty well with your exact dynamics now, even in 2 dimensions, right? And again, that can be even brought into some sort of mean field in the infinite connectivity limit. But now again, kind of coming back to Sarang, here you see this periodic trajectory and this one and this one and that one. So are all of them important, right? Are all periodic trajectories equal, or how to kind of distinguish them? And for that, we need indeed a different measure. We need the so-called quantum leakage or instantaneous norm loss of my wave function, right? And that's something, yes? Well, that's locally how bad my mean field theory is. So I can ask, right, I have my tangent space, and I'm projecting my exact evolution onto this tangent space. And there is some norm, right? There is some disagreement between exact evolution and my projection. So I can quantify this norm very effectively in thermodynamic limit using still MPS machine. And that's actually one of surprises from Harvard trajectory, right? You see not only that it's periodic trajectory, but it's somehow lucky to go in the region with a minimum loss, right? Because if it would go here, your wave function would leak very strongly, and your quantum wave function would just leave your variational manifold. Instead, if it goes in the region of low loss, what happens is that it stays there. So something that one can do, one can actually conjecture a lower bound on a quantum fidelity from the fact that your MPS has a periodic trajectory with a low leakage, right? And low leakage, again, is a key, because here I'm bounding my fidelity density. It's a fidelity per degree of freedom after some finite time. And it's bounded by this integral of my leakage. And this bound is not really tight, as you see here is a numerical check. So here I'm deforming my scar by some nasty perturbation. And this nasty perturbation, what it does, it deforms my trajectory, but I have Km that protects my trajectory. So Km says the trajectory cannot become unstable immediately. Here, trajectory vanishes only here, where I stop my plot. But you see that this leakage, initially a bit decreases. So actually this deformation for weak strengths, it can stabilize my trajectory a bit. But after that, you see that leakage grows in both directions. And again, criterion would be that, roughly speaking, when this gamma reaches something order 1, you see that my ED data stops collapsing onto each other. That means that this quantity is actually not even well defined, right? I assume that this guy has a nice thermodynamic limit. It looks like it indeed has it from numerical data, and here, all is gone, right? So that's kind of the lesson, that even though periodic trajectory perfectly persists on this side, and actually your phase space surprisingly gets even more regular, you have even bigger Km tori, you don't care so much about size of your Km torus, but something that is much more important is leakage. And now, kind of in the last 5 minutes, let me go to the worst case scenario, right? Let me take my thermalizing transferred field Ising model, right, and ask, okay, it's thermalizing, chaotic, bad. Is there something like this happening still here? And for that, I'm using, again, ansatz, which incorporates entanglement. Now 1 unit cell ansatz. I have 4 variational parameters, but I have 1 unit cell ansatz. There are 2 tensors, and you still do TDVP, you still recover mixed phase space, and you find this periodic trajectory, which I'm now showing very tiny zoom of Poincare sections. And now we fixed energy density to be here. And you see this is an entanglement plot of a finite size model. So you see, okay, no scars here, right? Hopefully that is kind of convincing. Entanglement entropy of eigenstates as a function of energy of eigenstates, everybody is kind of typical, right? Now, obviously, this model is very chaotic, so TDVP has a strong leakage. So actually, it will fail at time order 1. After time order 1, entanglement grows so badly that this small bond dimension TDVP is useless. Again, still, never hurts to try, right? So still we kind of try, and what we see is that even though TDVP fails, there is a certain correlation between entanglement at late times and leakage. So this is, again, one axis shows leakage, another axis shows entanglement. And okay, you may say it's not so spectacular, but still, this model is taken as a canonical model of thermalization. And now we choose slowest versus fastest initial states. So these are states, we're not comparing apples with oranges. These are states which all have the same energy density, and they have all the same initial entanglement, which is not 0, but very, very small. You see it doesn't start exactly from 0. And we ask which state grows entanglement slowest and which state grows entanglement fastest. These are 2 guys. And now you try to collapse, right, according to this ansatz. You shift them by a constant time, just in case you may say, oh, maybe this ansatz has a constant time delay, and you collapse entanglement by a system size. You see that, again, they saturate to the same value. So in some sense, they still relax to the same thermal state. But you see that, again, to me, looks like the velocities are not drastically different, but they're markedly different, right? There is a different velocity of entanglement spreading beyond my error bars, at least in this system. If I would do the same thing on a PXP model, I would get slopes different, by 40%. So, and I can still, I would deform my PXP model to the extent that no scars are visible, and I would get markedly different slopes. So again, the message is that perhaps maybe no such a notion of really universal Lieb-Robinson velocity, which is defined once and forever, at least in the local Hamiltonians, right? Because local Hamiltonians, by necessity, would have some of these periodic trajectories, and somehow surprisingly, even though they are high leakage, right? So TDVP is useless around here, right? TDVP would predict that entanglement would oscillate like this forever. Entanglement doesn't oscillate like that forever. It shoots up to the sky. Still looks like this variational manifold has some deep internal structure, right? It's not arbitrary Hamiltonian system. It knows about locality, perhaps. It has some interesting hierarchical structure which says that leakage at low times somehow seems to be correlated with entanglement even at high times. Again, that's maybe a hypothesis and some first kind of type of evidence, but I think mixed phase space is a kind of interesting player in this game, and maybe it can lead to a non-universal thermalization even in kind of conventional thermalizing systems. So with this, just let me kind of conclude. 3, 4, 5 years ago, I would go around, give a talk, and show ergodic systems, integrable system, MBL phase living here. Nobody corrected me really that this is kind of a pathological thing, right? There are systems with mixed phase space on this side, right? If you take a few body systems, they're never kind of fully ergodic. There is always mixed phase space and would be some funny periodic orbits in them. So conjecture is that some of this carries over here, like people did it in a few body quantum chaos, and here it would give rise to slow thermalization, right? Quantum scars have a lot of interesting connections. People are exploring connections to quantum Hall-inspired models, block models. It's interesting to think if it's related to different sources of ETH violation, like what Marcos Nidarich was doing and other people were doing. Again, connection to integrability is not explored. This model has a weird zero-mode manifold, which is exponentially degenerate. If it has anything to do with this physics, we still don't know. Some interesting connections to me look about trying to push it to a strongly entangled scars, right? Have trajectories which go through high entanglement region and kind of return back. And maybe using it in some practical cases. And something else, right, would be nice to build this dictionary being inspired by a few body systems, because there people really worked out a number of consequences of mixed phase space. You would see mixed level statistics, you would see different statistics of wave function, stability to perturbations, dephasing would be different, and so on. What does this, what from these guys carries over to these trajectories, right? If your system has this now many body trajectories which are weakly leaking, what of these consequences would carry over there? And also kind of linking this triangle, right? Entanglement growth, Lyapunov exponent in this TDVP manifolds, and TDVP leakage, right? Again, also a lot of other people are thinking about how to link these three guys, right? That also something would be exciting. And maybe this analytical TDVP approach, right, where you can really see the equations and you can really obtain almost all properties until the very last step analytically may be helpful in this respect as well. So with this, let's just show conclusions. First part for eigenstate aficionados, right? Special set of eigenstates, SU2 symmetry. Second part for those who like variational dynamics, mixed phase spaces, TDVP. Even in case of strong leakage, we still seem to find some slower thermalization. Of course, would be really great to connect these two. Can I take this trajectory and make from this trajectory embedded SU2 representation? Or even better, can I take some tiny, leaky, very bad, poor trajectory and enhance it and make a proper scarf from this very poor, but quite exotic trajectory where my observables would do some crazy things on it, right? And with this, let me just acknowledge people without whom this research wouldn't be possible. Dima, Abanin, Zlatko Papic, Alex did most of the variational stuff. Postdoc at IST, Chris is now also a postdoc, did mostly of exact anglization and deformation stuff. And deformation story was joined with Harvard people when Wei was here, Sun Won, Anne Spichler, and Misha Lukin. Just let me show my conclusion once again and ask for the questions.
Thank you very much. Questions? Yes, please.
this revivals
Yes.
in the picture. So what is the prediction of the series? So I guess they will slowly go down the amplitude of these revivals. They should not be really.
So if you have this perfect deformation, the prediction would be that revivals are forever. Revivals are stable in thermodynamic limit and they are forever. Of course, as soon as you add weak deformation, your revivals will be decaying.
Can you calculate what is the decay rate of these revivals?
I think that's an interesting open question. I think it probably is going to agree with some sort of Fermi golden rule type estimates, but it's certainly, I'm not aware of anybody doing this right now. So again, I think it's an interesting question trying to understand from this ideal SU2 embedded stuff, right, what happens once you apply deformation. I think something similar was done recently by Anusha and Motrunic, but they didn't consider this scarred states. They considered some special zero mode state and asked about Z stability. So they asked about stability of one perfect isolated state. One can also ask stability exactly about this whole SU2 ladder, right? There is this SU2 ladder. What happens to it? So I would expect something like Fermi golden rule, but would be good to do explicitly.
Other questions? Yes. Yeah.
Why when you do the mean field ansatz, you only allow for angle on this direction, the theta angle? Why not?
Yes, that's a very good question. That was there is a hidden symmetry which I kind of swiped under the carpet. You are totally correct that a proper spin, right, must have two canonically conjugate variables, theta and phi. And I was able to discard this phi. And that has to do with so-called flow invariant subspace. This flow invariant subspace comes from asymmetries in my model. Roughly speaking, intuition is that my Hamiltonian has only sigma x term. So if my all spins are pointing up or down, they have no chance of tilting off this equator, right? If if I have magnetic field along x, right, all my spins should be rotating on this thing. That's kind of intuitive picture. That's why if I prepare states which have no phi equals 0 is a stable manifold. So on phi equals 0, you would find phi dot equals 0. And it means that if you're in this manifold, you never leave it. So that is a symmetry, but you are correct that symmetry may be broken, and I showed it very quickly, but for two-dimensional lattices, I broke that symmetry, and it still works. There you have legitimate four-dimensional phase space, you have phi 1, phi 2, theta 1, theta 2, you still have the same business.
Check.
So, Max, I have the impression you use the term leakage in two distinct ways. First, there is let's say, the deviation from the periodic trajectory inside, but still inside the TDVP manifold. No, that's
no. I never. Again, maybe it was not clear, but I tried. Leakage for me is the only thing that I mean by leakage is leaving variational manifold.
Right. Okay. So then I think my question is a different one. So then the non-mixed phase space.
Yes.
What was that meaning? Was it meaning that you were that the motion on the manifold was completely dominated by these periodic orbits? By some Nekoroshev theorem?
What do you mean by non-mixed phase space?
Well, because later you went to mixed phase space, but before you went to mixed phase space, arguably you had non-mixed phase space.
Well, again, before I was looking at this two-dimensional case, which was considered by Harvard people, and there I don't think it's mixed phase space is expected, right? I think there is a qualitative difference, right, between two-dimensional phase space, three-dimensional, and actually four-dimensional also. There is, 1, 2, 3, 4. There are like 3 different classes. I think in 4 and beyond, you have something like Arnold diffusion. In 3, you cannot have that. And in 2, you don't have even a mixed phase space.
So non-mixed means all tori, all periodic orbits.
Well, again, you see two-dimensional flow is very weird because two-dimensional flow, if you look at it, it doesn't, proper model in two-dimensional flow, it would be kind of just regular flow. Right, that model has some singularities, and the flow is really kind of what's happening to the flow is the flow really depends on the singularities, and let me again just maybe quickly show it. So, right, you see that there is a singular point here, and all trajectories that are here would fall down into this essential singularity. And there would be a basin of attraction of different singular points. And this basin of attraction is exactly separated by this periodic trajectory. And people claimed it unstable. I'm not sure actually, one has to be very careful about its stability because it may be marginal actually, because I would expect that flow here deviates, but then later kind of comes back to it. So it's not even clear if this would even have a proper Lyapunov exponent in this case. Again, it's two-dimensional, everything is special, plus this nasty essential singularities make life very complicated.
Okay, so I think we should move on. So let's thank again.